Okay, can you guys hear me? Can you see the screen?
Yes, we can see it.
Thank you. Okay. So my name is Anushka and I'm the AI and blockchain lead at GDSC. And today we're going to do the first session in machine learning. I'm going to cover both theory and implementation. And our first model is linear regression. So in this series, other than linear regression, I'm going to cover different classification models. There's k-nearest neighbors, naive Bayes, logistic regression, SVM, and there might be more. Then clustering is an unsupervised learning algorithm, and then neural networks, data pre-processing steps that we'll do in the implementation, each one of them, and deployment, meaning how to, once you've done your model, how do you put it into production level so that other people can access it, and auto ML tools on the cloud where you don't have to like hard code all of it. So today we'll start off with the basic idea. Then there are three concepts that are cost function, gradient descent, and normal equation that involve the mathematics. That's basically how the whole algorithm works. Then evaluation metrics is how once you built it, how do you evaluate how good it's doing? And then before we get to the implementation, we'll just go through a list of things that you should like go step by step. And then we'll do the implementation in Python. I'll be using Jupyter Notebooks for that. And because we're covering a lot of stuff, we'll have a little recap in the end. Okay. So, as I said, we're doing a lot of math, so I don't expect you guys to like understand everything as soon as I say it, because I myself, I watched the same 1.5 hour lecture like 5 times, and I took over a week to get this whole thing done. So, I'm recording this session, and I'll share the resources that I used to learn it, so you guys can choose whatever you want and spend some time on it, practice it after the session. So you can, everything that got in your head stays, okay? So we'll start off with graphical representation because that's the best way to understand ML algorithms as beginners. But obviously, computers don't do stuff like that, right? They cannot generalize, at least fundamentally. I mean, with AI, we're trying to get generalization, but like humans, if I just show you a graph like this, um, you know that, I mean, you can tell that at this point, y is equal to 0. And then when we go up, this is the maximum value of y, and now it's going down. Even without any numbers, you can tell the general trend of things, but computers work only with math. So we're going to go through the mathematical aspect next. That involves some calculus, a little bit of matrices and vectors, but I'll try to simplify it. And then finally, the application, of course. Actually, in the application, you don't need to know any of the math or anything at all. You don't need to hard code the whole thing. You just import it from TensorFlow, or today we'll use scikit-learn, and you just make an object and send it your data and use dot predict function. And like that's it. But most of the work goes into understanding the whole process, getting the data, preparing it to put it into the model, and then doing stuff with it later. Okay, so let's start. This is the slide from the deep learning part that I did, but I'll just go over it quickly for someone who has no idea what this is about. So suppose our task is to predict house prices. Our data set is going to have price and some features that affect it. So right now, we'll just take this one feature called the size of the house in square feet. So this is the graphical representation. All these data points are house prices and the price of I mean, house prices and the size of the house mapped on, okay? So what linear regression does is it just draws a line through this data. As you can see, it has a linear design, right? So it draws a line through it, which is called the best fit line. And you might have learned the line equation in high school math, probably, y is equal to mx plus c. So this line's equation in math is y is equal to mx plus c. So x is what we're giving it, like our inputs, and y is what we want it to predict. And the algorithm's job is to come up with m and c, like these are called the parameters, right? So other than input and output, these are the parameters, m and c, and that's our linear regression model's task. So in this line, suppose I tell it to I give it an input of my house being 1,500 square feet, and it's going to give me a price of about $250K. So, yep, that's what linear regression is. So remember some points before we go ahead. Linear regression gives numerical output. You give it numerical input, it plots it, and it gives a numerical output. Because um, this graph is just, we've shown it from like 0 to 2500 and all, but it goes till infinity. And our model gives us a definite, like a proper number in an infinite number of possibilities. So from here, it could be 100K, it could be 200K, it could be a million, and it just goes on. But because of this line, it's giving us a proper finite value. Okay, so to understand how it works, some algorithms start off with just randomly choosing values for M and C, and then just taking small steps and seeing which one is correct, which one is not, which direction should we go to. So suppose I draw a line like this. This is completely wrong, right? You can see that it's the exact opposite of the linear relation. But our algorithm can start off this way. And what it does is it sees its error. Like from all of these points, it sees how far its prediction is from it. So this line is our prediction, and all of these points, it calculates the distance from it. Like here, 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 like that. So it calculates how far it is from each actual point to its prediction, and that's what residuals is. It's basically the difference between the actual value and the predicted value. Okay, this distance. Each one of them has its own residuals. And now in this, we just have like 10, 12 points, but usually in normal like production level, we have hundreds and thousands and maybe tens of thousands of points. So it doesn't make sense to like just list all those residuals down. You want to put it into like one metric so you can understand how far are you from the actual ideal position of the line, right? So that's what a cost function is. A cost function is just summing up all of these residuals. So y cap means predicted, means whatever y we predict using our line, and y, just y, is our actual value. So y cap minus y, we're taking the difference in between them. We're squaring it because we don't want to see whether it's plus or minus. We just want the number. So y cap minus y, the whole square. And then we just sum it up. Okay, and this half is just, it matters for further calculation. Don't worry about it right now. So cost function is basically one number that represents how much error you have in your line right now. And it's not an evaluation metric, it's used within the algorithm. We have different metrics. After you train your model, you use some other techniques to like see how much error you have and do some other things. Cost function is used in the algorithm itself. It calculates cost function and it does changes in itself. Okay, so now we get into the math. So our aim here is to find parameters that minimize the cost function. Parameters is M and C, right? So we find parameters that bring the error until like, if not zero, at least minimum as much as we can, right? So find parameters to minimize the cost function. Now there are a couple algorithms or techniques that we use to do this. Optimize, in the sense the dictionary definition of optimize is just changing for better efficiency. So we're just doing something to the line, changing it up to make it more efficient, to make it do its job. Okay, so we're going to see two algorithms, that is gradient descent and normal equation. Okay, these three are just types of gradient descents. We'll go over that later. So first we'll go over the graphical representation first. Okay, I'll start with gradient descent. It's an algorithm that linear regression uses to get to the right parameters. So as I said, gradient descent starts off randomly. Like M and C, it just chooses maybe zero because it can be positive and negative, right? So usually we just choose zero. Okay, M is zero, C is zero. And we start off with like this random line. And this is a graphical representation of here's M at our y-axis and C at our x-axis. And then cost function is the z-axis. So we're visualizing for different values of M and C, how high is our cost function. Don't worry about these like limits over here, 0, 1, and all that. It could be anywhere. It could be minus 100, plus 100, or whatever. Okay, we're just graphically, we can't show the whole thing. So it's just limited to 0 and to 1 here. So looking at this graph, you can say that these red parts are probably where the cost function is the highest, which is maybe around 0. And then the lowest, or actually this one is probably the highest. Maybe. Yeah, this one should be around 2. And the lowest is the dark blue part over here, which should probably be like minus 3, right? So what gradient descent does, let me change the color so you can see it properly, is it starts off at a random point, right? So maybe I'll choose here. Okay, this random point means like a random point M and a random point C. And this is the corresponding cost function. Okay, so I need to take steps to lower the cost function. It takes small steps. It doesn't reach this point directly. So learning rate over here is the length of steps that it takes, in the sense, like this, like this, like this. If it has to go towards that minimum, then this length is like fixed. That is called the learning rate. So let's think about it step by step. Suppose this much is my learning rate. I could go in this direction. I could go in this direction. I could go in this direction and some other ones, but let's stick to these for now. That's my learning rate. And these are the different directions that I can go to. Which one is going to bring my cost function down the most, minimize the cost function? So over here, this one kind of looks like it's closer to the yellow, right? So I'm going to move here. Okay, and then again, these are the steps I could take. Which one seems to be the lowest cost function? This point maybe? It looks like it's in blue. So I come down here. Okay, another time. I'll do it again. I come here, another time, and we reach the bottom. So step by step, gradient descent starts off randomly, and then learning rate is the length of steps. Takes that many steps, and it comes down. Now you might think that why are we taking such tiny steps? If we could just like jump here or maybe take 2 steps or something with a big step, we'll reach it quicker. Why are we doing so many steps? So what happens if we take a big step? Let me show you. Suppose I take this length of a step, okay? So I did once, I did it twice. Now, as you can see, the step seems to be larger than the distance from our point right now to that minimum distance. So what it does, it comes towards it, but it goes somewhere else. It can't stop down because the length of the step is pretty big. So it goes in another direction. It has no choice. It's diverging from our minimum. It reaches it, but it can't stop there. That is the issue with having a big learning rate. So learning rate is usually like really small, like 0.001 or 0.0001, really small. Yes, it takes many steps and it takes a little time to get towards the cost function, but at least we don't go far away from it. Okay, gradient descent is a really important algorithm because it's used throughout machine learning, even in deep learning, as you will see later in neural networks and all of that. So yeah. Another algorithm is normal equation. What normal equation does is it doesn't take step by step, it just directly finds the right values for M and C. So you might ask me, if there is a way to directly find it, why are we going through all this mess, step by step, gradient descent, blah, blah, blah? The answer is that normal equation sometimes doesn't do the job as fast as we expect it to. It might sound really fast, but it takes time to compute. If you see I'll show you the mathematics in a little bit. So if the data points is like really large, like the professor that I'm learning from right now, he says if it's like about 10,000 data points, then normal equation starts becoming really slow compared to gradient descent. So that's one disadvantage. So normal equation is the best algorithm to use if we're doing it with a small data set. But if it gets really big, we'll probably choose a version of gradient descent. Okay? So uh, let me talk about normal equation first. I explained that gradient descent is step by step. Let's see how normal equation finds it directly. Like we'll talk about the basic idea first, then we'll get into the exact math. So while learning about normal equation, I remembered a technique that I learned back in high school math. So let me give you a little recap of that as well, because I had to like go back to old high school math to understand this. Okay, so if you maybe you remember that in our functions chapter, either in your first year of university or back in high school or something, we did a chapter called functions where where some of the questions told us to find the maxima and minima of a function. If it doesn't ring a bell, it's okay. I'll just go over all of it. Okay. So our aim today is to minimize the cost function, right? That is, find the minima of the cost function. So what we learned back in high school is being used here. It's a real use case. So let's go over the basic definition of a derivative, and then we'll find how to find the maxima and minimum. So the definition is slope of a tangent of a function at a point. Let's break that down. Suppose I have a function over here, something like this, okay? A random function, I just drew it. And this is the graphical representation of it. Slope of tangent of a function at a point. So let me choose this point randomly, okay? At this point, tangent, so whether I'm coming from here to here or here to here, it doesn't matter. My tangent is going to look something like this, right? Sorry for drawing it badly. I'm drawing on the laptop, so yeah, something like that, right? So we chose a point in the function, we do a tangent on it, and it says derivative is the slope of that tangent. So this is the slope. Now we can, if we have like the angle and all, we can use trigonometry to find this out. But our definition says mathematically, you can just derivate it and that will be the slope at that point. Okay. So let's just go ahead and see how to find maxima and minima, because today's aim is to find find the minima of the cost function. In the sense, find the minimum of the error that you can make. Okay, number one is derivate the function once. So let's take an example, random example of a function. Derivate it once. So if you derivate it according to the rules, this will be 0 because that's a constant minus x square will become 2x. So our answer is 2x, right? Okay, I'll just remove the 0. 2x is our answer. Second step, it says equate the derivative to 0 and find values for x. So if I equate this to 0, to get rid of the coefficient, I can just multiply on both sides and then these will get cut. And anything with 0 is 0. So the value I got for x is 0. In some cases, you get multiple values, but here I just got 0. Okay. Next step, it says test values that stand between these points with the derivative and see which answers are positive and which are negative. What that means is test values that stand between these points. In the sense, the range of numbers are from minus infinity to plus infinity, right? The only point that I've got that might be a maximum or minima is x is equal to 0. So test values between these points. In the sense, our range is going to be between minus infinity and 0 and between 0 and plus infinity. So I need to pick points somewhere there. So let me pick minus 1 and plus 1. Okay. Okay. So it says test these values with the derivative. In the sense, I'm going to plug it in here. So f dash of minus 1 and f dash of plus 1. So the value we had gotten was 2x. So let me do that. minus 2 into minus 1, which is equal to plus 2. Okay. Same thing with plus 1, minus 2 into plus 1, which is going to give us minus 2. Okay. So we've gotten two values, that is plus 2 and minus 2. Next, so it says see which are, oh sorry, see which are positive and which are negative. So one is positive, one is negative. If answer for 1 point is positive, and after passing the x value, it turns negative, this means that x value is a maxima. What does that mean? We saw that one is minus 2, one is plus 2, right? So let me show you graphically. Let me use the same kind of function again, like this. Okay. So at this point, just forget about this for now. See the graph. Here you can see if I'm going in this direction, as I'm increasing y, as I'm increasing x, y is also increasing, right? At this point, x is probably like, let's say 1, and here it might be 5. At this point, it is maybe 2, and here it might be 6. It's increasing, basically, both ways. So this is called a positive slope. So this point, it is positive. But if we take this other side, here we're increasing y, but we're increasing x, but y is decreasing. This is called a negative slope. So what we're seeing here is the pattern of these, whether it's positive or negative slope, because derivative means slope of the tangent, right? So one part is plus and one part is minus, in the sense initially when x is equal to minus 1, it's positive. When x is equal to plus 1, it's negative. So we're going from like minus to plus, like well, we're increasing x. In the beginning, it's positive, later it's negative. Here, you saw that here it's positive, here it's negative. So this means that this point that we got x is equal to 0, that stands between x is equal to 0, that stands between minus 1 and plus 1, is a maxima. Over here, you can see that if the slope moves from positive to negative, then it passes through this maxima. This is the maxima, right? The highest point of the function. And this is minima. So if you see that the slope is positive and then negative, it means it's the maxima. And that's what we're seeing here. Initially, it's positive. Later, it turns negative. That means x is equal to 0 is a maxima. Similarly, if it was the opposite, if our initial value is minus, like negative, and then later if it was positive, it would mean that this point is a minimum. That's what's written here. If answer from 1 point is positive, and after passing the x value, that is 0 in this case, it turns negative, it means it's a maxima. If it moves from negative to positive, it means x value is a minimum. So this is the concept. I hope you understand the relevance of derivation over here. We're finding the slope and we're seeing its trend. So we get whether that point that we found is positive or negative. Okay. Or maximum, sorry. Yeah, so this is what we learned back in high school. And we're going to use this. And this is literally what normal equation uses over here. Okay, gradient descent starts off randomly, step by step comes towards that minimum. Normal equation directly finds this minima using the technique that we just saw. We find the derivative of the function, equate it to 0, and then we see the trend. Okay? So that was the concept. Now let's actually do the math, like the derivation and all. I'll try to make it simple, I promise. Okay, so these are the starting equations. Don't freak out. This, what you see here, is y is equal to mx plus c. Okay, y cap actually. So prediction is equal to, let me say c plus mx. Okay, now we're going to call the prediction as hypothesis h of x from now on. These are the notations that you're going to see whenever you try to study linear regression in the future. Okay, that's why I didn't stick with the old line equation, and I'm using the ones that is used in linear regression. So y cap prediction is now going to be referred to as h of x, h standing for hypothesis, and all our parameters over here, like here it was m and c, right? Now it's going to be theta 0, theta 1, theta 2, and so on. here we chose a very simple example where we have only one x, right? Where x is going to be house size in square feet. But in real life, if you want to calculate house prediction, you'll probably take some more factors into account, right? What neighborhood is it in? How many bedrooms that it has? How many washrooms does it has? How many balconies does it have? Stuff like that, right? So there are many factors that contribute to a house price. So instead of x, it will become x1, x2, x3. So our equation is going to extend to like m2, x2, m3, x3, so on. That's what I wrote up here. Theta 0 plus theta 1, x1, theta 2, x2, and so on. Okay. You might ask, what is x0? Because the first one, c, is just alone. I just made an assumption over here that x0 is equal to 1 so that I can write it as a summation over here. So basically, this notation over here means that our line equation is the summation of the product of theta and x. I just wanted to write it in a concise way because if we have many x values, many inputs that we're giving, then it'll just be really long, right? So this notation, it just means theta and x each like from 0 to whatever number of input values we're giving. We're multiplying theta and x and we're summing it up. And we're just assuming that the first x0 is equal to 1. The rest are all our input values that we're giving. Okay, so this is our line equation. Second thing, what you're seeing over here, this is our cost function. Cost function, what was it? It was the sum of residuals, right? Y cap minus y, the whole square, and then we sum it up, and there was a half outside. Same equation over here. Just from now on, we're going to say j of theta. Mathematical notation, okay? So this is cost function j of theta. Same thing you can see in here. Instead of y cap, I wrote h of x minus y the whole square, sum it up, and the half outside. Okay. So this is our cost function. This is our line. Now let's derivate this. Okay. So our step, we're learning gradient descent. This particular one, the whole name is batch gradient descent. So we go step by step, right? So what we do in each step is we take one of the parameters, we go one by one, all parameters. We minus alpha times the partial derivative of j of theta. Means we might ask, previously you told just a derivation and now you're saying partial derivative. Why are we doing partial derivative instead? The reason I'll tell you when we do the calculation. When we do the calculation, you'll only see why it just simplifies the whole thing. So we derivate j of theta, our cost function. And alpha is a really small number. I told you, right? It's the step, and we take really small steps. So we don't end up diverging away from that end minimum. So we just multiply this derivative with alpha. So the number is really small now. And we just minus that from the existing value of the parameter. So we're reducing the error bit by bit until our parameter comes to like a good value and the cost function is minimum. Okay, so let's plug in this formula into j of theta over here and see how the equation is. Just a few steps. As I said, try to follow up. If you don't, you can always watch this again. Okay, so it's theta j minus alpha of. Now I'll put this equation in place of j of theta, okay? I'll put the half outside, so I'll put it over here. Okay, now we do partial derivative. Sorry, I wrote it wrong. This is the notation. Instead of d, this is the partial derivative thing we use. Okay, in here, I'm going to simplify it for you. Let's just not consider sum at all. Let's say there's only one line of inputs. Usually I told you we have like hundreds, thousands, tens of thousands, whatever. In this case, just to simplify our mathematics, let's say there's only one line of like just one training sample. So I'll just not include the sum part. We'll put it back in the equation later. So we have this line and yeah, so this is the cost function, right? So partial derivative, if you don't remember what partial derivative is, let me just explain that a little bit for you. Normal derivation is like d of dx, right? Here it's with respect to theta j, but I'll just write x when explaining it. So suppose I have x squared, right? Um, you just, there's 2x squared, okay? You take the coefficient out, you apply the derivative formulas on x squared, it becomes 2x. And then we end up with 4x, right? This is normal simple derivation. Now, what part, suppose in normal derivation, suppose my equation was something like x squared y squared or x squared plus y squared. Then you'll have to derivate y, but you'll have to multiply it with dy by dx, right? Because it's not the same variable with respect to what we're doing. What if we had like plus z square, plus a square, plus b square, lots of more variables? It would be problematic, right? You don't know what to, it would just be a really long equation. So what partial derivative does, it just treats all the other variables except for the one we're doing with respect to as constants. In the sense, like suppose I partially derivate this with respect to x, we'll derivate x normally. Here x squared becomes 2x plus y squared does not have any x term, right? And I told you the partial derivative treats everything else as constants. So y square is a constant to partial derivation, and it becomes 0 because it doesn't have any x value in this term. That's the benefit of partial derivation here. You just, because we're doing it with respect to theta j. Now, if we have many x values, it's going to be multiplied with many thetas, right? Like here we have theta 0, theta 1, theta 2. It can go on into maybe 10 columns, 20 columns, whatever you decide to put in your data set. We'll have so many thetas. And if it's with respect to this one theta, theta j, like theta, like suppose j was 0, only theta 0. All the others will have d of theta 0 by, I mean, d of theta, whatever number, by d of theta 0. That would just be a really long equation and you don't know what to do with it. So that's why we use partial derivation. So we just treat those as constants. In the sense, all those will be ignored and we'll just see this one term. Ignored in the sense they will be equal to 0. That's why here we use partial derivation instead of normal derivation. It just simplifies the whole process. Okay, so here h of x, we're going to open up this into this equation over here. Okay, and to access it, there's a square outside, so let's derivate that. Equal to theta j minus alpha by 2, and then here's the derivation term, right? So I'll first derivate it, which is into 2 into this h of x minus y. And because this whole term is like some parts are with theta, some parts are not, like we have to derivate it again. That's the chain rule, right? So 2 and 2 get cancelled, by the way, and we partially derivate that line. So here, instead of writing h of x, I'll write the whole thing. So it's theta 0 x 0 plus theta 1 x1, so on. Let's just say it's just there till x1, okay, for simplicity. Plus sorry, it's minus, right? Minus y. We already dealt with square outside because we derivated it here. So we need to derivate this. Now it's all plus and minus terms. There's no square now. So we can individually derivate this. Now, as I said, suppose j over here was 0. Okay, suppose j is equal to 0. Our whole, let me clear this up a little bit. I'll just rub these old. I'll write it over here, okay? Suppose j was equal to 0. In this whole term, as you can, in this whole term, you can see that there's only one theta 0 here, right? The rest are theta 1 and y. Yeah, there's no other theta 0 term. So everything else will get cancelled except for theta 0, x 0. X 0 is 1, so it just becomes theta 0 in this case. If j is equal to 1, then theta 0 is not theta 1, so that gets cancelled. Y gets cancelled. Only this middle term, theta 1 x1, will remain. So basically, can we say that whatever value j is, only that term will remain over here when we derivate. So theta, obviously, the coefficient will come aside, and theta, that theta j is going to become 1 because that's how derivation works. So we'll just have 1 into that. We'll just have the xj term in the end of this whole derivation. So this is the whole step after derivation. You have theta j minus alpha. I added the sum back over here. We have the line into, instead of the whole derivation term over here, we have that line because we had 2 into the line and derivative of that line, right? So we have the line over here. And once we did the derivation on that line, we were left with only that one x value. So xj. Now, because the I and j is over here, don't get confused. It's written over here. I means all the X terms. In the sense, if you have 10,000 samples in your data, like 10,000 rows of data, then I is going to be 10,000. And J is equal to theta, like the number of thetas. Like in one sample, if you have house price, a number of washrooms, number of rooms, number of balconies, that's 4 different columns, right? Whatever number of rows you have, 4 different columns that are being filled other than price. So your X value is going to be 4. And we also have theta 0. So theta, the number of thetas is going to be 5. So I is equal to the number of samples you have, and j is equal to the number of thetas you have. It's written in vector form over here, but I hope it's clear. Okay, so to sum it up, I know it was complicated, but this is the end result of the derivation. So we have, let me say it again. We have whatever theta j, we start off randomly. We just make it 0. And then slowly from that value of that parameter, we minus alpha times this derivative that we calculated. Okay, so this derivative is the of the cost function. Cost function means sum of residuals. Residual is actual minus predicted. So we're summing up all the errors, we're derivating it, and we're alpha is really small, so we're making it into a small value, and we're minusing it from our parameter. So slowly we're minusing errors from our parameter, and until it reaches one value where the cost function is minimum. So that's what's written over here. Start off with all thetas randomly, usually 0. Iterate through all samples for one change in one parameter. In the sense here, you can see theta j is one of like whatever number of thetas, right? Theta 0, theta 1, whatever. We start off with 0, then 1, then 2. So that's what j is. So we take a single parameter for a single, and we go through the entire data set and calculate the cost function. And we do this derivation and do this calculation to minus that little bit of error from it. So for one tiny change to minus a very small amount of error in one parameter, we go through the entire data set, calculate the cost function, and do this step, derivation step and calculation. So that sounds like a lot of work, right? Yeah, but a computer does calculations pretty quickly. Gradient descent, this version batch gradient descent is a little lengthy, but it does the job well. As I said, it's used in deep learning and all. It's very important. Although it sounds pretty long and yeah, it does so many iterations. Yeah, but in the end, it does the job. So that's there. Now, as I said, it does so many iterations, so you might think it's going to be really, really slow. And with like really big data sets, it's going through such a huge data set so many times, it's going to take too much time, right? So there is another version of this gradient descent that is, okay, we'll talk about that later. Just see how it starts off. Like suppose I make all my parameters 0, that's how we start, right? And then we take tiny, tiny steps. So this will be the initial position, and then later slowly it moves into position like this until it reaches a point where the error is minimum. So before we get into the other types, let me show you how much time, how many iterations we're doing here. So questions, I hope it's okay if you can't answer it, but just try. Take this situation. Suppose we have a house prediction data set of 10,000 rows. Okay, it has 4 columns: price, size, age, neighborhood. So price is going to be our y, right? The prediction that we want to make. And size, age, and neighborhood is x1, x2, x3. Okay. So can anyone tell me how would h of x look like? How will be the equation with these three parameters? I mean, these three inputs. Does anyone know?
Sorry, I don't know.
Okay, it's
No
okay.
idea.
Yeah, it's okay. Okay, so h of x look like theta 0 x 0 plus theta 1 x 1, theta 2 x 2, like that it goes on. Over here, we have three features that we're calculating. Other than price, our prediction, we have three: size, age, and neighborhood, based on which we calculate price, right? So h of x is going to look like, we have theta 0 always, and then we have x1, x2, x3. So it's going to be, x0 is just 1, so I'll just add it here. Theta 1, x1. Okay, we have three x values, right? So theta 2, x2 plus theta 3, x3. This is our line equation. Three values three input values, and then its parameters plus the 0. This is our line equation. So that's the answer for the first question. Second question is, how many rows do we iterate through to change all parameters at once? So let me remind you what I told last time, so you can like try this one. So I told you to change a single parameter once. It goes through the entire data set, calculates the cost function, and does the calculation and minuses a little bit of error. So to make this one change, it went through the whole data set. So to change all the parameters, in the sense all these thetas once, how many rows do you think it will go through? Any idea? One parameter change it goes through the whole thing, and I told you the whole thing has 10,000 rows. So for all these thetas, how much time do you think, I mean, to change once, all of them once, how many rows do you think it will take?
40,000?
Exactly. Yeah, you're right. Yeah. So one change is going to take 10,000. So, and there are four thetas. So 4 into our size is 10,000. So 10,000. So it's 40,000. Right. Great. I didn't actually think anyone could answer so quickly because it's so complicated. Great job. Okay. So as you can see, so many iterations, right? It goes through the whole thing so many multiple times. That's going to take a huge amount of time. So the solution we have to that is to tweak in something in this gradient descent. We'll talk about that normal equation later, okay, where we reach these values directly. So stochastic gradient descent it uses the same method, but it does one thing. Over here in this equation, if you can see, there's no summation over here. Usually we would add up all these like values. This is for one single sample, and we would like add all these samples up and then, do the derivation, blah, blah, blah. So what this means is that this change is being done with taking only one sample in mind. We're not going through the entire data set. We're just doing one. It picks the first one. It changes this parameter. It changes all, like, suppose in previous example, we had like 4 parameters, right? It changed all of them based on that one sample. Then it went to sample 2. It changed all these parameters based on sample 2, based on the error in sample 2. Then 3, then 4, it goes to the whole, every single row. It changes all the parameters for each row, and it goes to the whole data set only once. So from 40,000, we went to 10,000. That's great. Okay. So instead of iterating through the entire data set for updating one parameter once, we just take one sample, update all parameters, and move on to the next sample. So one by one. Okay. Now this is faster, but it has greater variance. Now, what does that mean? It means that now all house prices, I mean all these prices, that whole data set you got is not like perfectly it doesn't have a proper pattern, right? It's not like how a line looks like. In the sense, like some people might have a pretty house with like nice woodwork done inside and they'll sell it for a lot. Some other person might be in a hurry and they'll just be like, whatever customer, they're not good in negotiation, they'll just sell it for some small price. So there'll always be this variance in the whole thing. Even in our line, like in our plot that we saw, they weren't aligned in one line properly. They were all over the place a little bit, but I mean they had the shape, but it wasn't perfectly in one line, right? We're always going to have some amount of cost function because of this. There's always that variance. That's why I said minimize and not bring it down to exactly zero. So in stochastic gradient descent, you're taking every single value and and making changes based on it. Previously, we kind of took the whole thing together, so any up and downs would probably be mixed into it. But here we're making a change on every single one. So it's all sometimes it might take when it's taking these steps, it might take a slightly different direction because because of that single data, like that line of data being either too high, too low, something like that. So it's not a huge problem in the end because a majority is going to fall into a certain range, right? You can't always sell something at a really high price. You're likely, most majority are likely to sell it in a small range. That's why we have that linearity. So it might diverge a little bit here and there when it's coming towards that minimum value, but it's gonna come eventually. It's not like it's a good algorithm, it's fast. It's ideal for like big data sets because you can't go through it so many times. And although it has a variance, it just happens sometimes and it comes back eventually in line because majority of them follow that path. Okay, so we had three types of gradient descents. We had batch gradient descent, that went through it multiple times. We had stochastic gradient descent that makes changes based on each row, so it goes through the whole thing only once. Now, a third type, we're just going to mention the title. We're not going to go through the math because you get it by now, right? So there's also mini batch gradient descent that takes n samples in one batch instead of one in SGD. What does that mean? In gradient descent, normal one, like batch gradient descent, we go through everything one for each change. And for stochastic, we go through just one sample. Mini batch is in between these two. We don't go through the whole thing. We don't just take one into consideration. We take like bunches of it, like batches, mini batches. Like if I take 10,000 and my n is like 100, I go first 100, second 100, third 100, like that. So instead of every single sample, I'll take a bunch of them and calculate it. So as I said, that little variance is going to get mixed up in that. So it's nice. So SGD, stochastic gradient descent, is used for very big data sets. Gradient descent can be used for smaller ones, or we can use that normal equation. I'll show you that next. Gradient descent is the basic step by step, that whole concept. Stochastic is a practical version of it for a big data set. It's used, and mini batch is just in between. Okay, so that's it for gradient descent. Now let's get into normal equation. Normal equation, we're doing the same thing we had done last time. I mean, I had explained where you equate the derivative to zero, derivative of the function to zero. You find the value for x and you see whether it's like plus or minus and all. So let's do that calculation. This is matrix multiplication and derivation. You probably have not come across derivating a matrix. So I'll show you the formulas. If you don't understand, again, it's okay. Like we're just derivating it. We reach an equation. We'll see. Okay. So we're representing all of our parameters, values, everything in terms of matrices now. Okay. That's how the calculation is done. So x of I is like one sample, like one row in your whole data set. So it has like x0 is 1, but I'm just including it. Then you have x1, x2, like probably size, age of the house, neighborhood, all that stuff. So one row, all the values in one row, x. Now, capital X is going to have all of these. So it's basically like how you would have a table in Excel. Okay. Now what transpose, if you don't remember what that means, is it just turns all the rows into columns or columns into rows. Like suppose like now I is shaped like this, right? So suppose I have 1, 2, 3. Okay. What transpose is going to do is just make it into a row. Okay, 1, 2, 3. Now instead of like 3 columns and just one column in 3 rows, it has 3 columns in one row this time. It's just from this shape, it turns into this shape. Okay, so each one is made into like this shape, like one row, like how a table looks like. It's all stacked upon each other. So your so this X has your entire data set that you're giving it, your whole training data set, except for the Y part, okay? Y is your prediction one. So you're keeping that separately. Again, Y is just a list of all those prices, like that column. So X is that part of your whole table where all the features that contribute to the price, and Y is the price itself. And then we have theta, that's all the parameters, okay? So how would the calculation look like? H of x, the line equation, this was the old line equation. Now we'll just represent it as x and multiplication of the matrix x and the matrix theta. So if you remember how matrix multiplication was, um, each value of the row, like here, is going to be multiplied with each like column. So x0, theta 0, x1, theta 1, x2, theta 2, go on, and it sums it up together. So same thing as we had done for the line, right? So again, it's all in matrix symbols. But we're going to represent it like this now, x and theta, just multiplied. And j of theta, our cost function, instead of this big thing, we're just going to have we're going to write it like this. The 2 is there instead of the summation and h of x, all of that. We're going to have the line was x theta, right? Minus y, so it's our predicted minus the actual. And instead of square, you can't square matrices, right? You do it in multiplication. And there's a transpose here. So what it does, like if you just write x theta minus y into x theta minus y without the transpose, you're going to end up multiplying, like suppose here there's first x0, x1, x2, okay, another row x0, x1, x2, okay, and y is looks like this. You're going to multiply, oh wait, it's theta, right? Let me just explain it simply. You're going to multiply a row with a column. You're going to multiply different values together, basically. But transpose, like suppose, let me write it out like this, simply. So you know that this matrix is a transpose of the first one, right? This is the original, and then if you take the transpose, it's going to look like this. So if you multiply, if you multiply the transpose of a matrix with itself over here, it's going to be this into this into this, 3 into 3. So transpose with its original is gonna like literally square it. That's what we want, squares. If you just write x theta minus y, x theta minus y, it's gonna multiply different values together. It's messed up. So transpose it makes it multiply, it's multiplied with its own value. Okay, so it's like a square. Okay, sorry for the messed up explanation. So let's do the calculation. We'll just simplify this once and then we'll derivate it, okay? So once these formulas on the side are what we're going to use to do the calculation. You might have seen these two maybe, but these two you probably haven't because this is derivation. Now, this symbol that you see over here is just a partial derivative. Okay, I just wrote it in a concise way. That's because the professor used it like that. Okay, so these are four formulas that we'll do today, or that we'll use right now. Okay, so to do this calculation, to open up these brackets, okay, we're going to take, how do you open brackets? You multiply each term with each other and then minus this term with this term, this term with this term. That's how you open brackets, right? So that's what we're going to do. First, let me just open the t's, open the transpose. We have transpose on the bracket. So if we try to remove this, we'll put the transpose in each term, like that, like that, like that, each term. And then we do this multiplication. So this is how it looks like when you open the brackets, like xt theta t multiplied with x and theta. That's what we've written here. Xt theta t with x and theta. So each term we multiply it, this is what we get. Okay, next step. Now we need to derivate this, right? And if you let's see these derivative formulas that we use. Number one, theta t, it's all with respect to theta, okay? Theta t ax. In the sense, we need two kinds, we have two kinds of formats. Here, one is theta t ax and the other one is theta at. If you want to simplify this, it means if the term with respect to what we're derivating, like here it's theta, if that has the transpose, then it becomes 2. Okay, if you do the derivation, you get 2ax. The coefficient stays as it is, and this theta transpose becomes 2. Okay, that's one pattern that it follows. The other one, if it's our coefficient that has the transpose on it, and theta is just theta, then our answer is just that coefficient. Okay, so these are two derivation formulas. Just like in normal derivation, something raised to like an exponent value, you're going to take that exponent and that value to, like suppose it's x squared, you do 2 into x raised to 2 minus 1, which is just 2x, right? So it's just another formula like that, but in matrices. So let's just work on that a little bit. Okay, so here if you see these two terms, these two, okay, you can see that these two, x theta y, x x t theta t y, sorry, okay, and the other term over here has y t x theta. In the sense, in this, other than y, the other two terms have transpose, and in this next term, only y has it and the others don't. So let's try to like make these two same, so we can just add it together. So make one term less, okay? So we have a formula for that. A transpose B is equal to B transpose A. Second rule over here, okay? Second rule. So it means either one can have the transpose. The multiplication is going to be the same. So what we're going to do is we're going to turn one of these into, like, we're going to transfer the transpose into the other term. That's what we do here over here. So this term, okay? We make only y have that transpose. So over here, we cut these two and we add the transpose to y, just like how this formula has. Okay, that's one change that we do. Another one, this term comes exactly as it is. Okay, this one, both of these become the same. So we have a 2 over here. We add these two together, okay? So it's minus of this term, minus of the same term. So it's minus 2 of that term. And then y, we just y transpose y, we just cut it off here because we're doing derivation. Okay, at this point we apply the derivation, and this doesn't have any theta value. Partial derivation, right? Any term that does not have a theta value, it's just a constant. So I just remove that at this step. Now here we need to apply these third and fourth formulas over here, right? So, oh, sorry. What is happening? Okay. Okay, sorry. So we're in this step and we need to do the derivation. We need to use 3 and 4. So let's bring our terms into this format. Here, in this first term, we have a theta transpose. And we have a formula for theta transpose, right? If the term theta transpose is there, everything else is going to remain as it is. That term is going to turn into 2. That's it. So if we derivate this term, it's going to become theta transpose becomes 2, and then the rest is just the same. So xt is there, x is there, theta is there. So this term is dealt with. This is going to be the derivation, partial derivation. Okay, now the second one, we have theta, but the rest aren't in transpose, right? Here in the fourth one, you have theta without the transpose, but the rest of the coefficients have to have the transpose on it. Here, one y has the transpose, x doesn't. So we need it to have the transpose. What do we do? So we're going to use formula number 1, where 2 transposes means the same matrix. So what we do is we'll add a transpose on this and we'll add another transpose on this. So if we write it in another way, we're going to have this line. Okay, we have the transpose over here on x, and then we have it in the bracket, so that all the coefficients came in the bracket, and we have theta. So this time, this is going to turn into 2 into, we just have the coefficient in the end, right, in the formula. So it's just going to be x transpose y. Whatever's in the bracket is going to stay as it is. That's what we did. So next step over here, that's what we wrote. Okay, this turns into this because we use the third one. And then here, we apply this whole formula. We put t on this, another t transpose, and then we derivate it according to number 4, and we get this term. Here, we have a theta t already, so we just directly apply it, and we get this term. So we have 2 everywhere, and we had a half outside, so we cut all the 2's, and we get the answer. Okay, so we get this answer from this line. Okay, and previously we saw that after the derivation, you equate it to 0 and you get a value for your for theta over here, right? Previously it was x, but here we're talking with respect to theta. So we have this formula in the end. So we have this in the end. We equate it to 0. Okay, so here I'll bring this term on this side because it'll be positive on both sides. So we have this. And then finally, our aim is to get theta, right? So we bring this to the other side down, which is going to be inverse. So this is our final formula. Theta is equal to, this term is over here, okay? And this term that we brought to the other side, this has the inverse sign on it. Okay. So basically, we had the line formula, we had all of that, and we did the derivation on these matrices, and we got this as our theta in the end. Okay. So this step, this method, normal equation, did no iteration. It just did all this calculation and it got theta directly. What's the issue with this? As I said in that previous slide, for larger data, it looks really simple, but if you think about it, X is the entire data set. Like if you have 10,000 rows, it's going to be 10,000 into maybe, suppose you have 10 columns, it's going to be into 10. This is a really big matrix, right? So if you actually do this calculation over here, this term, it's that gigantic X matrix and another X, that same huge matrix, multiply them together. You've probably done multiplication on 3 by 3 matrices, and it takes a little bit of time, maybe 5 minutes. So on this size, it multiplies together. And if you've done the inverse of a matrix, again, involves a couple steps, right? You do A of IJ, something like that. So step by step, you have a couple steps to follow, even in the 3 by 3 matrix. So here, calculating the inverse after multiplying these gigantic matrices, it takes a long time. It looks like a really tiny equation, but it takes a really long time. So that's why it is slow for large data sets. In the second term, takes time to be computed. Therefore, stick with stochastic gradient descent for big data sets. Okay, so we're done with the math, literally. So let me just sum it up. You learned gradient descent. You learned 2 types, batch, which is the simple version. Okay, and then you learned stochastic, and then you learned normal equation. Okay, gradient descent, step by step. Stochastic basically just does it on each sample instead of going through the whole thing once. And normal equation comes directly, but it takes a long time to compute matrices of all these steps. And that's why you use stochastic gradient descent to go through the whole thing once, and it's much faster than normal equation or normal gradient descent. Okay, so these are the algorithms. These are the 2 types of algorithms. There are many, but these are the two main ones that is used to get the parameters for linear regression, to get the line. Okay. Okay. So once this is the last slide that involves some amount of math. Okay. Once you're done with the whole process, you get values for theta, all the thetas. How do you evaluate your model? Meaning, this is what you're going to see. These are the metrics that you evaluated with. Cost function now was done for making like the whole algorithm in the process. These are made after your whole calculation, everything is done, you get the line, you get the prediction. How do you know how good your model is doing? Okay, so you have four metrics over here. Sorry. Coefficient of determination. This squares the correlation coefficient. If you know what that is, then it's just the square of that. And the definition is it shows how much of the variance of y is explained by the variance of x. Don't worry about it. Let's see the math, and I'll go back to this line. Math is 1 minus RSS by TSS, where RSS is sum of squared residuals. In the sense, it's literally how the cost function is calculated. You take all the residuals, square see the difference. You take actual and predicted difference, that is the residual, square it and sum it up together. So sum of squared residuals, same thing, okay, as the cost function, by TSS, which is the squared sum of actual minus average of actual values. In the sense, like see this graph, okay? Our highest y is somewhere around 350 maybe, and our lowest has a y value of like maybe 50K. So if I have to like take an average of this, I might take like 200 maybe. Like in this, the middle looks like around 200, right? So let me draw a line around 200. So this is our average of the actual values, right? So if I see what it says is actual minus average of actual. So we take these y values, all we have, and see the difference from the average. In the sense, just like how we did for residuals, you see how far they are from each other. So let me just draw it. Okay. Now, if you see this, can you say that these actual minus average of actual, the difference looks much more than the residuals, in the sense actual minus predicted? In this case, the line is drawn properly, and it kind of looks like our actual minus average of actual, this red thing that I'm drawing here, looks like it's going to be more. Squared sum is going to be more. So if we have a good model, then RSS, our errors, sum of squared errors, is going to be lower, it's going to be small, and TSS is going to be large, right? Okay, so if we have RSS as a small number, TSS is a kind of bigger number, then you're going to get 0 point something, because it's a small value divided by large value. So you're going to get some 0.123 or something like that. And coefficient of determination is 1 minus of this division. So 1 minus 0 point something, 1 or 2. If it's a good model, then it's going to be a small decimal. So suppose it's 1 minus 0 0.1, you're going to get 0 0.9. So that's what's written here. Near 1 means better model. So if we calculate coefficient of determination, we don't calculate it, we just ask for the value in the coding part. And if the value we get is near 1, like 0 0.8, 0 0.9, 0 0.7, at least if it's like closer to 1, then it means our model is doing good. Now, if I draw a line that's like this, okay, the exact opposite of a good line, then that you can already say that the residuals are going to be much larger than this actual minus average of actual. So RSS will be big and TSS will be smaller comparatively. And we're going to get a bigger number because it's a big value divided by small value. And 1 minus that is, you can get either a really a really big decimal, because RSS by TSS is going to be a proper big value, not a small decimal. And you're just subtracting like 1 minus of that. So either you're going to have something like 0.01 or something, in the end, or even a negative value. If it's that bad, then it's going to be like far away from 1, like maybe 0 or -1 or even lower. It could go really bad. But basically, if it's a good model, you'll get somewhere close to 1. And if it's a bad model, you're going to get somewhere far away from 1. So the aim of correlation, coefficient of determination is, now we're seeing the variance in actual minus average of actual. You're seeing how up and down it is. And even in squared residuals, you're seeing how far away we're from the actual values after prediction. So it's variance in y and variance in like x, like a prediction and variance in actual y's. So what coefficient of determination tells us when we see it, when we see the number, is we'll know how correlated are y and x. In the sense, your input values, how related are they to y? In the sense, like in our example, suppose house prediction, we have price, and I give you information like age of the person living in it, or the number of people living in it, or the income of one of the people in the household. Like it's all irrelevant compared to size of the house and age of the house, all that. Age of the person doesn't matter that much, right? So if we give irrelevant data to our model and we tell it to predict y, it's going to do a bad job, and we'll get a coefficient of determination that's far away from 1. So this number we use to calculate how related are the two. Okay? How much variance in y is explained by variance in x. We just compare the correlation between x and y. That's what this metric tells us. So this might be a little complicated, but just know that basically it shows the correlation between the two. If you get a really bad one, you should probably change your data. The rest are just summing up the residuals pretty much, or averaging. So the first one, it says mean absolute error. Average difference between predicted and true values. That's it. So instead of like squaring and adding them up, you're just averaging it. Okay. Second one is mean squared error. Means before taking the average, you square each residual and then you take the mean. Last one says root mean squared error. So like you have all the residuals, you square it, you average it up, and you take the root of that. So they're very similar. They're basically giving you the amount of error you have. You might ask, why are they so similar and what's the difference between them? They have some factors, but if I have to say it in the simplest way, in mean absolute, we're just averaging it up, and in the others, we're squaring it. Now, squaring a value makes it a lot bigger, right? So if I take 2, 2 is like 2, and then if I square it, it's 4. Same thing if we have the value 4. 4 is 4. Square of 4 is 16. So the more you square the numbers, the bigger they become. So in mean squared and root mean squared, you're squaring your residuals in the sense you're punishing them. You're showing that the errors are large. So maybe if you want really small errors, if you're making a very important prediction, which involves maybe lives of people or something deadly, temperatures, something like that, then maybe you might not use mean absolute, you'd use the other two, one of the other two. But that's like a simple one. There are many factors. I'll go through them maybe some other time. But for now, just understand it all represents how much error you have. Okay. So in this slide, we went through two types of metrics. The first one, coefficient of determination, tells you the connection, the correlation between the input data you're giving and the prediction you're asking. And the rest are just summing up, averaging the errors and stuff. That's it. We are done with the whole theory. Okay. We'll go over everything we did in the recap, but for now, let's get into the implementation. Okay, 1 second. Okay. So before we get into the Jupyter notebook and actually code everything, let me just go over the general steps you follow. First, to import modules. Today, we're going to use sklearn, okay? And we're going to also use pandas and matplotlib, which we had learned in last session, to deal with the data before we put it into the model. Okay, so import them, then you load in your data set. Okay, I chose one from Kaggle, again, the same website that I used last time. Then pre-processing steps if required. I'll explain what that is in our data set when we work with it, okay? Because we do some steps before we put it into the model. Then you split it into testing and training. What that means is if you send all of your data, then how do you evaluate it? Thing is, if you evaluate it on the same data set after training it on the same data set, it might perform well because it's already seen it. But then if you give new values, it'll probably be bad. That's what overfitting is. We'll learn it later, but I'm just saying it. So you don't want to test it with the same values that you've already shown it. It's like in exams, like if they want to really see if you've understood or not, they'll probably give slightly new questions instead of the same thing that you've solved in class, right? Same thing over here. Training and testing, we take our data set and we just split it. Like maybe or usually we take like 80% for testing or 70% for for training. Sorry, training. We take a majority of it for training and we leave like 20 or 30% for testing. Okay, so validation is another type. We're not going to do that today, but validation data set comes between training and testing if we choose to do so. And validation is to make changes in in our model. Today we're not going to do that, but obviously after we make our model, after the algorithm is run, that's not the end of it. Obviously there's some things in the module that you can tweak in to make it better. Other than our data, whatever we give it, correlation, blah blah blah, there's some parameters that we can give into the model that we can how we can improve that model. So validation comes in when we're trying to do that. And that changing, tweaking, whatever, it's called hyperparameter tuning. Again, I'll put all this lingo in another session, but I'm just saying it for now. So training is what you send in the data fresh in the beginning to train it. If you want to make changes and you want to like improve it and all, then you make validation and you test it on the validation, then make changes, blah, blah, blah. And then finally, in the end, after you've done all your changes and you're ready with your model, then you just test it and give some evaluation metrics. Okay, so that's one step. Then you create the model. After you split it into these three, ready to give it to the model, you make the model. Okay, you have already imported that object. So you just create the object and send it the data. Okay, so create it and then send the data to it, and it'll be ready. It'll be trained on its own. Linear regression does not take that much time, and we're using not that big of a data set today. Then you evaluate it after you're done. And last step, you try different data sets and models. Now, in this case, we're just going to use one model. But when we do classification next session, we're going to try different types of models, okay? And data sets, maybe like if you want to, as I said, training, testing, if you want more data, you can change that and try it out. Okay, so today what we're going to do, sklearn has two objects for performing linear regression. We have linear regressor, which uses the normal equation, and SDG regressor, which uses the stochastic gradient descent. Normal equation is equating to 0 and directly getting it. SDG is gradient descent, but with each training sample, and we just iterate once, right? So again, today we're not going to use such a big data set, so we're just going to stick with linear regressor. Okay, so I'm just going to import only linear regressor. Our task today is going to be prediction of life expectancy. Okay. And all the metrics that are in, like all the columns that are involved, all our features, X values, we have 21 of them. Okay. So we have country, year of getting, or year of that, all those metrics have been taken. Status of the country, whether it's developing or developed, adult mortality rate, infant deaths, alcohol consumption per capita, BMI, average BMI of the population, GDP, that is gross domestic product, percentage of GDP spent on health care, percentage of total government expenditure on health, then immunization coverage on on 3 different diseases, then measles cases, deaths that's caused due to those cases, under 5 deaths, deaths caused by HIV or AIDS, thinness in the age group of 5 to 9 and then again 10 to 19. Human Development Index based on income. Some other things also matter like schooling and stuff like that. But here we're just going to consider income and then schooling of average. So this is how our table looks like. Let's just get into it. Okay. Okay. So this is the Kaggle website where I got my data set from. Okay. You can download it over here. Over here. This is the CSV file. Okay. Okay. So this is my notebook. I'm going to start. Okay. So first importing all the modules. I'm going to import pandas as PD to deal with the data set. Pandas and matplotlib. Okay. Import matplotlib.pyplot as plt. And then we're finally going to import our object on sklearn. So import, oh, sorry. We're not going to import the whole thing, only that one object. So from sklearn dot linear model, import that object is called linear regression, right? Linear regression. Okay, I run this. It's all imported. Okay, next step, we load in those data sets. I put the URL over here. So let's load it in. df is equal to pd.readcsv. I'll send in the name of the data set over here with the path, because in this notebook is in one directory, right? There I created a file called datasets, and our CSV file is inside that. So I'm going to mention the file and the name. Okay, so it's life expectancy. That's spelling. Yeah. Okay. Let me run that if it comes properly. Let's see the data frame. Okay. So this is my data frame. So we have country, year, status, life expectancies over here, adult mortality, blah, 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 blah. Okay, it's the whole frame. We have almost 3,000 rows and 22 columns. It's 21 features, and that one column is our life expectancy. Okay. Okay, so before I use this, I need to do some pre-processing steps, right? Okay. So now you need to see your whole data set and see what problems it has, blah, blah, blah. To see which rows and what all changes you have to make. But I've gone through this whole thing, so I know it step by step. So, but if you're doing it yourself, you probably have to figure it out on your own, seeing how many values are missing, what is the format. So one issue that we have right now, very visible, is that country and status, both of these have strings in it. As I had told you before, in linear regression, you need numerical values so it can plot it, and then it can do calculations with it. You can't calculate strings, right? Derivation, all of that. It needs numerical values. So what we can do over here is countries. It has we have probably 193 countries, I think, in the whole world, and this has all of those. And yeah, so what I'm going to do, one way I can deal with this, it might not be the best way, but today I'm going to use it like that. I'm going to turn these from 0 to, I'm going to turn these into numbers, in the sense, starting with Afghanistan is equal to 1, and in the end Zimbabwe is going to be 192. So each country is going to have a number associated with it. Okay, so how do I do that? So I'm going to first pick okay, for I in range, length of df dot country dot unique. So df dot country is going to give me that particular row, and dot unique is going to give me unique values in that row. So let me just print it for you so you can see it. Let me print it first. Okay, and I'll comment this. If I run it, then as you can see, you have every single, uniquely, you saw in the data frame, you had many rows of Afghanistan. Here it's uniquely showing only one. So all the unique countries we have, yeah. So all of these are shown. So I'm taking all of these and I'm going to pick up like each one of them and say, put this number instead of this. How I'm going to do that is, so my for loop, I is going to be from 0 to 192, the numbers that I want to name each one of these from, right? So it's going to pick up each number and df dot replace df dot country dot unique. Here I'm going to mention that particular one. So like if this starts off with 0, right? So df dot replace, this is a function that it takes like two parameters. One is the value you want to replace. Second one, you'll put that value that you want to put in place of that. So replace the first whatever the first parameters it is with the second one. So here I'm taking that unique list that I got here, this array, and I'm saying pick up this ith one. So if I is 0, and pick up the 0th element, in the sense Afghanistan in this case. So it's going to pick up each country's, that whole column, that name, and it's going to change it to the next one I'm going to add as I. In the sense, it's just going to change it to that number. I is the number, right? So I. Yeah. Okay. One more parameter I'm going to add is in place is equal to true. What this is doing is, thing is, in many functions we use in data frame, like in pandas, you'll only know by observing while playing with this, okay? When you're trying to use different functions, you'll write it, it returns you the data frame looks fine. But later when you say printdf, you might see that that change hasn't happened. What that means is you've given that function your data, and instead of making it original, instead of making those changes in that original function, in that original data frame, it's returning you another data frame with those changes. So in place equals to true is going to solve this. So if you have that problem, add this in place is equal to true as parameter, and it's going to make the changes in that original data frame. So now if I run this, it's basically this line is going through each country. It's picking out that particular country by index, and it's replacing it with that index. So first one is going to be replaced with 0, second country with 1, on and on until the last one with that number. Okay, so I'll just show you how the data frame looks like now. As you can see, countries have been changed from 0 to 192. So all the countries have been changed to its corresponding indexes. Okay. So one more change is, as you can see, status is equal to developing and developed, right? It's written in strings. We need to change this as well. Now we clearly know that there aren't 192 values for this. It's the unique values are just developing or developed. Now there's another function you can use. It's called, there's another like syntax that you can use. df dot status is equal to, in this bracket, I'm going to mention the condition. So df dot status, if this is equal to the string developed, then I'm going to make it 1 dot as type int. So I'm putting a condition inside the bracket saying if my status is equal to the string developed, then what this is going to do is understand the syntax, okay? You're saying df is equal to df dot status is equal to, meaning the change is being done to status, and condition dot as type int. What this is going to do is if the condition in the brackets are true, then it's going to give the integer 1 to it. And if it's not true, it's going to give the integer 0. So basically, you're turning this column into ones and zeros. So if it's developed, it's going to turn into 1. And if it's not developed, it's going to turn into 0. So remember this syntax together, okay? You assign this condition dot as type int to that row, that column, And if the condition's true, it'll be 1. If it's not true, it'll be 0. Okay? So we've made 2 changes by far. We've gone through each unique value in the year column, each unique value, and we've changed it to its corresponding index in that unique value list. Second step we did is we changed developing and developed the status. We used this new syntax that you've seen to make it ones and zeros. Okay, based on this condition. So 2 changes have been done. Now there's one more change to make. Now you can't see it over here, but like when I was trying to write this whole code, I got an error later on when I was trying to create the model. Thing is, in all these, like in sklearn, if you send in a data frame with missing data, in the sense if some cells in the whole thing is empty, null value, nan value, whatever you call it, then it's going to give you an error. It cannot deal with like null values or nan values. So when I was trying to do this, I got that error. So I have to get rid of all the nan values. Now, how can we check how many nan values we have in this? So if I go through each, I have to like check each column. I'm going to go through each column. I'm going to see how many null values are there, and I want to change it. I'm going to use that a function called fill NA. You might have seen it in last class. Fill NA basically means everywhere we have NA, like nan values, fill it with this parameter that I'm giving you. So for I in df dot columns, I'm going through each column, okay? df dot columns is going to give you an array of all the column names. So for each column, okay, before I do this, let me show you how to check for nan values, and then we'll make the change, okay? So suppose I choose, let me check adult mortality maybe, or let me check hepatitis B. Okay, hepatitis B is over here, right? So let me type in that hepatitis B. So this is it's going to give me that row, that column, right? So let me see if it has null values. So right is null. This is going to give me true or false. If it is null, it'll be true. It'll give me a list of true and false. If it is false, then it means there's some value there. If it's true, it means there is a null value there. So I can't really see this. So let me use dot unique again so I can see whether it has a true or not. Dot unique. If I run this now, see, if it has no null values, it's the array is going to be full of falses. So here I would get just false, but here I'm getting a true as well. This means that there are some null values in this column. And like that, I checked each column and like it's there in many columns. So what I decided to do is I'm gonna go through each column, and I'll see if there are null values. And if it's there, then I'm gonna use fill NA function. So if true in df, that particular column, here we're going through each column, right? So if that column dot is null dot unique dot unique, this is the same thing that we used last time, but that we used just now to check whether it's there or not. We got an array of true or false here, right? So I'm checking if true is inside this array. If it's true, then it means there are some trues over there. There are some null values. So if it is there, then I'm going to use dot fill NA, fill the non values. I'm going to give it a parameter, some value that I have to fill in. Now here, I'm going to make an assumption that if there are some null values in hepatitis B, it means that the countries just haven't done that scheme at all. Now this assumption shouldn't just be made. Usually, if you're working on something real, you should probably go to the source and ask them, like, why is this place empty? What should I put in place? Would it make sense for a zero, or should I just remove the whole row? What do I do? But here we're just testing stuff, right? We're just doing it for learning purposes. So I'm just gonna assume that it's zero. Do not make this assumption in real life. Confirm it with someone's, with an authority or wherever you got this data from. But for now, I'll just fill all the null values with zero for convenience, okay? Again, I'll add in place is equal to true. So I don't end up not doing this at all. In place is equal to true. Okay. So this whole part, I'm going through each column. I'm using a dot is null dot unique to get whether there is a true or false, whether there is a true inside that array. And if true is in there, then I fill all those null values with zero. Okay. Again, this is an assumption. Do not make assumptions blindly. Just for now, for convenience, I'm doing it. Okay. So now I'll run this and I'll do the same check now. Over here, I had checked hepatitis B, right? Let me check it again. So you can see whether there's a difference or not. Hepatitis B. So now I run it. Oh, I made a spelling mistake here. Why isn't it running? Is that an error? Oh, right, it ran. It just took some time. Okay, so now after this step, I'm checking the same thing that we did last time, and now it's showing only false. So it means there are no trues inside. Okay, so we successfully made all the changes. Now we have no null values, we have no strings, we've changed all of that, and we have our whole thing ready. Okay, so next, I can just make the thing now. I can just start off the whole thing, but let me just do one more step. I can make the model now. Let me make one more step. Let me see if there is a linearity, like a linear shape to our data set. Because that's an important thing. You can use linear regression only if there is some linear relation between x and y, right? If it's like all over the place, if it's all scattered, then making a line is not going to do a good job. So let's see if that shape even there. Like in our PDF, I mean, in our PowerPoint here, as you saw in all the examples we saw, there is a linear relation. It's not fully straight, but it's there, right? We're just checking if it's there in our data set as well. It's important. If you know that it's there, then it's cool. But today, I mean, you just saw the data frame today, right? So let's check it out. What I'm going to use is I'm going to use matplotlib and just plot all the points. So we see whether it has that shape or not. I'm going to plot each column with respect to, I'm going to make each x-axis as values of each column. And I'm going to make y-axis as life expectancy because we're seeing it with respect to life expectancy. In the end, we want life expectancy as our prediction, right? So for I in df dot columns, here I'm gonna remove life expectancy because I want that to be y. I don't want to compare life expectancy to life expectancy. So for this, I want all the columns should be x values except for life expectancy. So let me just drop that. So to drop, I'll use dot drop columns is equal to life expectancy. Okay. Okay. So I'll first do this and then I'll C dot columns. So this df dot drop, this whole line is going to give me back a data frame with all the information intact, except it just removes life expectancy. Okay, so I'm taking all those columns now. Okay, so plt dot scatter. Last time we used plt dot plot, which gives you a line chart. This time I want to see each point. I don't want to connect them together. So I'll use the scatter function. Okay, in here I want each column as X, and I want a life expectancy as Y, right? So, okay, okay. So this, I gave it X and Y, and now I'll just add labels to it so we can like see which one is which. So if you remember the functions, it was X label and Y label. So X label, I'll give it that particular column. Okay, I is going through each column, right? So call is that. Oh, I write column here. Okay. So each graph for each plot, we're going to see the x-axis as that column. And I want all the y's to be the life expectancy, right? So I'll add y label as life expectancy. Label. This time I'll add life expectancy. Okay. And then finally we add, we add plt.show. We should always add this in the end. Okay, so I'll run this. And I'm going to get a bunch of plots for comparing each column's values to life expectancy. So first one is country. Obviously here you won't see linear relation because we changed it up right into numbers and all. Okay, here it's scattered, but you can see that compare this part. You can see that before we had many countries with the life expectancy of 40 around 2000, and then 2014, like 10, like more than a decade later, our lowest life expectancy is around like 45 maybe. So like generally there is a slight slope over here, and we can see that it's improved comparatively to 1 decade back. So before applying any machine learning thing, you just have to see your data and see the pattern and all of that for just basic understanding. Or this is called data analysis, right? Before doing the machine learning part of it, you have to understand your data. So that's what we're doing right now. Okay, life expectancy with status, either developing or developed. As we can see, all the developed countries have a higher life expectancy rate, while developing ones, some of them are like really low. Next, we have adult mortality. Clearly, we have this line linear relation over here, but it's a negative slope, obviously, because it's adult mortality. Here also we can see a slightly negative slope. It's a little scattered. I mean, it's a little all over here, it's crowded, but a few points we can see it has a shape. This with infant deaths, of course, it's going to be negative. Here it's pretty scattered. It's with alcohol consumption, nothing much. Here also nothing much. Percentage expenditure. Next we have immunization. Here, as you can see, in the in the countries who have done better jobs, it's more scattered over here. Life expectancy is fairly high. Then measles cases, nothing much over here. Here you can, it's still scattered, yeah. BMI. You can see a negative slope sort of over here. It's with respect to under 5 deaths, of course, negative slope. Here it's slightly linear, you can say, positive slope. That is with polio. Yeah. Okay, it's scattered over here, developing. I mean, the ones who have done it, life expectancy is like crowded or more on the top. It's good. This is quite scattered. It's with total expenditure. Here, there is a kind of linear relation. It's with respect to another immunization thing. Here, it's inversely. I mean, not inversely, it's negative slope. So, of course, with deaths caused by these diseases, it's going to be negative. Here, a little bit, but not much. It's with respect to GDP. Nothing much. It's all crowded in one place here. Population. Here, we can see like a negative slope. It's with respect to thinness, of course. Then here also similar negative slope. It's thinness in another range of kids. Here, very clear positive slope, linear shape. It's income composition of resources. It's that human development index in terms of income is that. And then very clear linear positive slope with respect to schooling. Okay, so we saw all the plots. Clearly, some plots have a linear relation. So we can try linear regression here, right? Okay. So before we create the model, we're going to split the data sets into training and testing. Second. Okay. So we're going to divide it into X and Y first, and then we'll do X test, Y test, X train, Y train, and all. So we have X and then we have Y. Yeah, X is going to be all the columns except for life expectancy. Oh my bad. Yeah. And Y is going to be only that column with the life expectancy values. So it's df dot drop columns is equal to life expectancy. Okay, so all the columns except for that one column. And then Y is equal to only that column. So it's going to be df life expectancy. I'm adding the gap each time because I checked the list of columns and the name has a gap in it. That's why I'm adding a space over here if you noticed that. Okay, so I've divided into X and Y, and now I want to cut it into like I'll choose 70% and 30% as the training and testing division. Okay, so we have a function in sklearn called test train split. So we're going to use that. I imported only linear regression object, right? So I need to import this one as well. So sklearn dot model selection import train test split. So we're importing that one function. Okay, so I'm going to divide it into there's X train, X test. I'm just giving names, okay? Because we need to assign it to 4 different variables. So Y train, Y test. Because our function is going to return 4 of these different things. So I'll call the function now train test split. And then I'm going to give it X and Y. So it splits it for me. X, Y. And I also need to give one parameter called test size, which is basically how much of this data set do you want for testing. So I told you I'm going to I have decided that I want like 70% for training and 30% for testing. So for here, I'm going to put 0.3. So 0.3 of that data set is for testing. Okay, so I'll just print X, like Y test for you. Okay, so as you can see, we had like 3,000 rows, and now after this division, Y test has only 882 rows. So majority has gone in Y train, and it's all been split up. Okay, cool. So we did the split. Now we can go into before we create the model, there's one last pre-processing step. It's called scaling. Now what scaling is as you saw a data frame, a lot of the values are like varying, right? For example, country went from 0 to 192, the range of values. Then the status went from 0 and 1, 0 to 1, like developed or developing. Then the other values were like, it's all over the place, right? It has different ranges. And the issue is that if we have such a big variation, like suppose I'll give you an example. Suppose we have 1 to 20. Is that a big range in your mind? Maybe you'll be like, no. But if you think about like the calculation we did, we're making really, really tiny changes. So maybe like 0.0 something. So if we go like into the decimals and we like go step by step like that, then you can see how many steps that gradient descent would probably take to reach from 1 to 20 if 20 was that parameter value that we want. So even if it's like a couple integers, it's not that it doesn't seem that much. Gradient descent will like take many, many steps to reach that. So imagine if this range was from 1 to like 1,000 or 1 to like 10,000 or something. It's way too much, right? Like populations are in millions. So is it going to like go from here till there? It's too much and it's going to take time. So what scaling is it basically brings down all of these numbers into between 0 and 1. All values that we have, it's going to bring it down to a value between 0 and 1. It doesn't affect us because we're not going to scale y, because y is the number we want. If it's going to give a value between 0 and 1, you'll be confused. So we'll only scale x values, like the whole data set that we're not trying to predict. We're giving it in because it doesn't give importance to like the exact value. It's seeing with in comparison to the others. Like price, it's going to see that for this square feet, for this, like for 1,000 square feet, it's like this much. 2,000 is this much. So like there's this much difference between these two. And it's going to like do mathematically like that. It's not seeing the exact number. It's seeing the variation and the trends. So whether it's from 0 to 10,000 or 0 to 1, if it's scaled properly, then it can get the trend just as well. So what we'll do is we'll change each one into 0 and 1. Now we don't have to hard code this. We're obviously going to import another method that just does the job for us, okay? So from sklearn dot preprocessing, import standard scalar. There are different ways of scaling, like different values you scale between. Standard scalars, it does standardization, and it basically means bringing all values between 0 and 1. Okay, so we're going to create a scalar object, standard scalar. Okay, we've created the object and we'll send in our x values. So I'm going to scale x. I'm going to scale each x variable we have. We have x with the whole data set. We have x train with the training part of it, and we have x test with the testing part of it. So I'm going to scale each one of them because we'll refer to this later for valuation and all, right? So I'm changing each one of them. So x train and x test. And I'll change each one. So the formula is scalar dot fit underscore transform. Oh, okay. So I send in the data like x, and it just I'm reassigning it to x. So it's the scaled version of x now. So for each one, I'm going to do the same. But of course, I'm going to send the original one. So x train over here, then x test. So each x variable we have with x values in it, all of them have been scaled between 0 and 1. Okay, if you want to see it, then I'll just print it. Oh, I don't think it. 1 second. Maybe I did a typo. Yep, typo. Over here it's E. It should run now. 1 second. Oh, capital. That's a typo, I'm sorry. Okay. Okay, so as you can see now, it's all 0 point something. Yeah, it's scared. Okay. So let me just run everything again in case I ran some particular cells improperly. So we did all our pre-processing steps now. It's all done. We'll get to the real interesting part. It's just creating the model and getting the prediction. Okay. So I'll name the model regression model, like reg model. And I'll create the object first. Okay. So I made the model now. And to train it, I just need to send it the data. So regression model dot fit is the function that we use to send it the data. So I'm going to send it x train and y train. Okay. And it returned me the object. So yeah, we're done with the model. as I told you, you don't need to know all the math and all, but it really helps. And when if you want to do this as a career, and then when you go for roles and stuff, research, all of it, you need to know the math and everything under the whole thing. But to actually code it, you don't need to know anything. So yeah, so we have made our model, we trained it. Now let's get the prediction. So we'll take the model, reg model dot predict. So I'm going to give it like our X test values. And it gives me an array of all the prices that it can, yeah, we got it. This is our prediction. Cool. Now, obviously, I can't go through each value over here. So what I'm going to do is I'm going to evaluate it with the metric that I'm going to use today is MAE, mean absolute error. So it's just taking all the residuals and taking the mean. That's it, that value. So again, okay, there are two things that we'll check. One is MAE, mean absolute error, and the other one is correlation, coefficient of determination, the correlation square. Okay, so one, I'm going to see the relation between like whether the data I've sent is relevant, and I'm going to see the number of errors I've gotten. So for getting the coefficient of determination to see the correlation, I just have to use this function, like model dot score. Okay, so I'm supposed to send it on my X test, obviously, and I'm going to send it Y test because it has to check with the actual values, and that's how it calculates the error, right? So I'm sending both, and if I run it, I got a 0.7, which is very, very decent because it's supposed to be close to 1, remember? So it's not far away from 1. It's not negative. It's not 0. It's 0.7, very close to 1. So we did a pretty decent job. Okay. And then there's, I said I'll check MAE as well, right? The mean absolute error, average of all the residuals. So for that, we need to import another function called cross-validation score. This is actually a different method of evaluation. You can do this without splitting our data set into test and train and all of that. So one way is to split it and then give it like that give it the training part to train and then the testing part. But another way to do this is we can give it all the data and we can just say that do it like this. I'll show you. So from sklearn dot model selection, import cross validations, cross val score. Okay, so this is the function like how previously we used score. We're going to use this to get our MAE. The MAE is equal to cross val score. Cross val score is cross validation. I'll tell you what that term means. Okay, I'm going to send it my model that will test it with X and Y. And I'm mentioning the score that I want, which metric I want, which is negative, mean, absolute error. Now, why I wrote negative instead of like just mean absolute error is if you go on this website on sklearn's like documentation, then this is the metric that they provide. I don't know why they put negative on it. It's basically negative of that mean absolute error, but that's what they provide. So if you check the documentation, you can get all the other metrics and what they are and all of that, including like the others like mean square error, root mean square error, all of that is over there. But today I'm just going to see MA, and it's giving me the negative version. I don't know why, but I'll just do it. Okay. Okay, and one more, CV is equal to 5. So what is CV? What is cross validation? So I told you this in this method, we don't split train and test and all of that. We just give it the whole data set and we tell it to do the job. what cross validation means is I said CV is equal to 5, right? So what it does, it's going to take, suppose I have 500 rows, okay? And I give 5 as the value. It's going to make 5 blocks of this whole data set. In the sense, if it's 500 total, it's going to make, each block is going to like have 100 rows in it. So it takes the whole data set, it splits it into the number of blocks that I specify. Here I wrote 5, so it split it into 5. And what it's going to do is it's going to train it on 4 blocks and then test it with the 5th block. And it's going to give me an MAE. It's going to train it on another flow blocks and test it with the next test block. What that means is, suppose I have like 5, okay? I want to test like which part of the data do I take? Because like suppose it's ordered by time. In the sense, suppose I'm collecting data from like the past 5 years to now. It's according to time and there'll be trends, right? So if I test it, if I train it only on historical data, it's not going to give me like for example, prices. Obviously, due to inflation, whatever product that I'm talking about, it's going to be more than last time. So if I give it only historical data, then it's going to like give me smaller values than what is like realistically the price today. So cross validation, what it does is, suppose I have like five blocks, it's going to do a combination in the sense it's going to train it on the 4 and then test it on the 5th. Then instead of taking test block as the 5th, it'll take it as 4 and train it on the rest. Then it'll take it as 3 and train it block 3 and it'll train it on the rest of the blocks. So basically, it's going to train it on different blocks, different time zones, and then, I mean, not time zone, like different time periods. And then it's going to test it on like a part of it. So it's going to like, it's changing combinations, right? So different out of 5 blocks, each time it's going to take a different block as the test data set, and it's going to train it on the rest and test it on that block it chose. So that's how cross validation works. And it gives you, and because I told it to make 5 blocks and do it 5 times, it's going to give me 5 different MAEs. So if I print MAE now, MAE, this the first one is the correlation one, coefficient of determination, and the rest are, as I said, I told it to do it 5 times, right? So it gave me 5 different MAEs. MAEs mean absolute error again. So we're getting negative is just the, I mean, I told you, we're getting negative mean square error, so forget about the negative. So we're getting 3.5, 3.9, 3.5, 4.3, 3.4. It's not that bad. Because a lot of the time I've gotten like -20, so it's decent. Okay. So as I said, 0.7 is a very good correlation. So we've done a pretty good job. So we did our prediction for today, but I just want to try one more thing. Let me see how many of these rows actually, or how many of these factors actually matter. In general, it's giving me the correlation of all of these together, right? But if I take like one specific row, like we saw in our linearity, like all those plots, some of it like have a correlation, some of it seem pretty like random, like all scattered and all. So I don't know if it matters really in this prediction. And if you have like a whole row which has no correlation to your prediction metric, then it's a waste. Why are you training it in so much data if it doesn't even matter, right? So let's see that. Let's see that. So I'm going to train I'm going to train a model multiple times and give it only one row and then test it with like a prediction. Do you get what I mean? Previously, we gave a whole data set with all columns except for life expectancy and made it predict life expectancy for us, right? This time I'm going to I'm going to like make a for loop and I'm going to give it only one of those 21 columns. So we're going to see if I give it only this one column, does it have a linear relation? Does it give me a good metric or like, I mean, a good prediction? Or is this correlation really bad? Does this metric even matter? Does this column even matter? Like that, okay? So what I'm going to do for that is, again, I'm going to iterate through, I'm going to make a for loop and iterate through each column. just like we had done previously for our plotting, like up here for this. Yeah. So here, I'm just going to copy this line. Okay. So I'm going to iterate through each column, and I'm going to do this splitting. Actually, I'm going to just show you how it looks like. It's probably going to take some time. Just some notebook that I like made ready. Okay. So this is the code I wrote for that. It'll probably take a while to like write the whole thing. That's why I just showed you. So for each column, I'm going to take one column, and X train is going to have just the a part of that column, and then X test will have the 0.3 of that column, right? So X test, I just divided the whole. Uh, yeah, I used a text train test split, the same steps that we did earlier. We fit it to that data, and I print the coefficient of determination for each one, and we used a dot score to get that, right? And then I want the MEE as well. So I do the same step, cross validation score. I send it all this information, and then I mention CVS5. Same steps that we followed. Only difference is instead of sending the whole data set, I sent only one single column. Okay. So I'm making the scatter plot. Okay. And see this line. This is the only new thing that you're seeing here. Dot plot. I want a line. Like last class we plotted line charts, right? So I want a line this time because I want to see the regression line this time. So I send it the x and y value, the x test and the prediction, and then I made it the color red so you can see it clearly compared to the points. So this is my whole answer. So first we did it with respect to country. We got a coefficient of determination as minus 0.003. It's like negative. It's pretty far away from 1, right? Alone. And because we changed it from like 0 to 192, I didn't expect anything anyway. So my ME is also bad. Previously we had minus 3 point something. Now we have like 7, 8. Pretty bad. Okay. Next we saw years. Here it's a little less, at least last time it was like minus 0 point something. Here it's 0.01, it's positive, but it's not that close to 1. So and I had previously told you that there is a kind of slight slope over here, right? So clearly we can see that there is some relation. It's not 0 below 0, but it's not that great. And again, our errors are not doing too good. Yeah, our line isn't that good. Next, we see status. Here, obviously, there aren't many points to see, but then it clearly has a relation. So our coefficient goes up to 0.17, better than the last two. Errors are again not in 8 at least, but it's okay. Last in our total in the full model we made, we got like minus 3 or something. That's great. In the worst one, we got minus 8. Now we're getting like 6 and 7. So it's like improving a little bit. And then here we clearly saw a linear relation. So our coefficient is 0.37. That's way better than the previous ones. But our total model did the best, right? It got 0.7. So here we got 0.37, better than the last few. Then our errors are still there, but it's way better. Previously we had 8 and 7, and now we have 4 and 5, right? Next, again, the linear relation is kind of slightly there. It's with respect to infant deaths. Here, correlation again is not high, but it's not negative. So there's a little bit, but not that much. And errors are, again are back to 7 and 8. Then is alcohol consumption. It's pretty scattered. There's not much of a linear relation here. So there is some relation, but not that much. So 0.212. And errors are in the range 6 and 7. Okay. Next is percentage expenditure. The correlation is 0.12. A little bit is there. And errors are still around 7. Then with respect to immunization of hepatitis B, slight relation, very small. It's clearly very scattered, so you can't expect much. Errors are still there around 7. Then measles, inverse relation over here. There is a slight one, errors. Then here there is quite a correlation, and errors are not 8 and 7 at least. Then we have under 5 deaths. There is a slight correlation. Errors are still there. Then this is polio vaccines. So a slight correlation, and errors are 6 and 7. This is pretty scattered, so obviously I didn't expect anything high. Errors are pretty high. Here it's there a little bit. So our correlation is 0.2, pretty decent, and errors are 6. Then HIV and AIDS, there is our line is clearly, I mean, it has a shape. So our correlation is 0.25, better, and errors around 6. Then here, nothing much, I think. Okay, 0.16 and errors are 6 and 7. Then nothing much over here. It's horrible, actually. It's a negative. Then this is thinness in a negative slope. There is a correlation of 0.2. And okay, then another thinness with a different age range, 0.13. Okay. Then income, very clear linear relation. It shows a correlation of 0.36, pretty decent. And errors are a little down now, it's around 5. Another pretty linear one. It's the last plot we have. And our correlation is 0.3 and errors are around 4 to 5. Okay, so we're done for today. So as you can see, individually they didn't do great. The maximum we came to is around 0.4, I think, 0.3 or 4. Minimum was like negative, pretty bad. But our putting them together, I think we did a pretty good job. We got a total correlation of 0.6, which is pretty close to 1. And our errors were like around, worst was -8 and all, and now we came to like 3. So yeah, this was our prediction today. We predicted life expectancy. Yep. Okay, so before we end it, let's just recap everything because we studied a lot today. Okay. Okay. Recap. So we started off with the basic definition. So what linear regression is it predicts numerical output from infinite possibilities with drawing a best fit line through the data. Some metrics we used are cost function. I mean, cost function is not a evaluation metric. It's used in the algorithm. The rest are R square, which is coefficient of determination, MAE, MSE, RMSE. Okay. Cost function captures the difference between actual and predicted values, and we use this metric to adjust the parameters inside the algorithm. Okay. R squared, that is coefficient of determination, shows how much variance in X is explained by variance in Y. Basically, the correlation between our input data and our output that we expect. Learning rate makes us take small steps towards the minimum of the cost function. This is used inside gradient descent, right? It's the length of steps. Batch gradient descent slowly adjusts parameters with the help of cost function and learning rate. It iterates through the entire data set for changing one parameter once. It goes through the whole thing. If there is a variance, it gets mixed up in between. It's a great algorithm, but again, it iterates too many times and it's slow. Very good algorithm used throughout the domain of AI, but it's slow with large data sets. Stochastic gradient descent changes all parameters with just one sample at a time, so it works much faster for larger data sets. As I said, the variance sometimes goes a little bit here and there, but it's still fine. It works really fast. And normal equation directly finds the minima without iteration. Here we equated the derivative to 0 and got the theta directly, right? But computation takes time as data set gets larger. So for small data sets below about 10,000, you'll use normal equation. For big data sets, you'll use stochastic gradient descent. Okay. Okay, so these were the equations you saw. This is the equation for a line. H of x is equal to theta 0, theta 1, theta 0, x0 plus theta 1, x1, blah, blah, blah. Then j of theta is the cost function where you see the difference between actual and predicted, square it and sum it up together. Okay, a single step in gradient descent was like this. After the derivation, you were left with just that particular x value and the line, you sum it up and you minus only a small part of it because learning rate is small. So slowly you minus errors and you reach the optimal value. And in stochastic gradient descent, we didn't have the sum at all. And in mini batch gradient descent, M was not the whole data set, but it was only, depends on you. If you set it to 100, then it's 100 or it's up to you. Okay, last one, oh my God. 100 or anything else, okay? It was written really bad. Okay, so the last method we learned was normal equation, which basically found theta directly without any iteration. And we did the calculation in terms of matrix multiplication and derivation. But the only issue over here is this term over here takes a very long time to compute because x is basically the entire data set, and we multiply it, we get the inverse of it. It takes a long time. Okay. So then finally you did the coding. You first imported the modules and then you brought the data set into like a data frame in your code. And then these were the changes we made to make it ready for processing. First, we used this syntax as type.int to here, if the condition is true, then it makes it 1. And for every other value is turned into 0. Okay. And then in these two lines, we iterate through each unique country value and we change it into that corresponding index. So from Afghanistan to Zimbabwe, we changed it to 0 to 192. Then in this for loop, we went through each column and we saw is null.unique means it's going to return is null is going to return an array of true or false, true only for those places where there is a null value, and dot unique just picks out the unique values, so you get true or false. If there are null values, then true will be there. So that's why I wrote if true in that array. So if it is there, then this happens. The fill NA function basically replaces all null values with the value you give it. So I replaced everything with 0. And therefore, we iterated through each column to see if there's anything, and we turned all the null values to 0. And again, it's an assumption. In real life, you have to check whether it's even allowed, if it makes sense with the data set. But anyway, so I did that because we're just learning. Okay, so we did all of this. We made the strings into numbers and all of that. It's ready. Just 2 steps before that. We check the linearity once because you should always study your data before you're doing anything with it to see if there's that linear relation and to see whether everything's relevant and all of that. Then you split it into test and train. For that, we use this function called train test split from sklearn.module selection. And then after splitting it and assigning it to these variables over here, we then scaled it. Scaling standard scalar standardizes your data in the sense it changes all the values to values between 0 and 1, right? Or like minus, I mean, it can be negative as well. So like -1 to +1, you can say. So we created an object and then we use the function fit transform to scale it. Okay. Then we created the model. We just called the object and then used dot fit to like send it the data. The main training is very simple. Okay, and we use dot predict to get that prediction. Finally, because we can't go through the whole prediction, we decided to evaluate it. Here, there were 2 steps we did. One, we get by dot score, we got the R square value in the sense coefficient of determination to see the correlation. We got 0.6 something, pretty decent, pretty close to 1. And then for mean, we imported cross validation score, and we mentioned that we want the mean absolute error. Cross validation again is an alternative to getting to dividing your data set and sending it apart and all of that. You just send in the whole data set and mention how many blocks you want it to be, and it just tries different combinations and gives you different MAE values for each one. Okay. So our MAE was like around -3, I think. Not that far from 0, so good. Finally, you always have to try different models, try different values and all. So I just iterated through each column and tried this method with each column. And I saw that individually they kind of have correlations. Most of them have something, but individually they didn't do that great, but together I think 0.6 is pretty good. Okay. So we did the whole implementation. Now, I learned this mainly from this Stanford lecture that was taught by Dr. Andrew. So if you guys want to learn that, then this is the link. It is a 1.5 hour lecture approximately. Again, because we did so much math and all, you probably didn't get everything in your head. If you are, then you're a genius. If you didn't, of course, this first link is our YouTube channel where we upload all our recordings. So this recording will also go there. And if you want another alternative, then this is it. You have the 1.5 hour Stanford lecture on linear regression. And yeah, so the next session is probably going to be next week, hopefully next weekend or next Saturday. I'm going to cover all these different classification models, and we're going to try every model in a data set and see which one performs best. And it's cool. It's very interesting actually, because there are like different ways to do this one, lots of different ways. Yep. So that's it for today. Thank you so much for attending. Please let me know if you have any questions, and hopefully we'll see you next week. So if you need me to repeat any part, if you didn't understand, please let me know. I'm free. I can just do it if you want, or you can see the recordings.
Hello, thank you for the lecture. My question is quite
Yes.
is linear used in real life? Like, I don't think linear algorithm works in real life,
They are
right?
used. I mean, it depends on your task. If you want to do like image recognition, all of those like more advanced things, then you probably won't use linear regression. You'll use more advanced models like the neural networks and stuff. But if you just like some companies just want a prediction of like it only predicts numerical outputs. So if that is your task, if you want to like predict your sales of the next quarter or like stuff like that, then if you want numerical outputs, basically any such use case, then yeah, you could use it.
Okay, thank you.
Thank
Have
you.
a good day.